have some goals. In fact, I have 3 goals. At this frequency, the transmission should be under 0.1. At this frequency, it should be over 0.97. And here it should be under 0.1. And now if you plot the error function with weight 1, you would find something quite strange. Because what you get here is, so I can plot a function. I have the inductance, I have the capacity over here, and what I would find here, if I plot the error function like a system of isolines, well, there is some optimum. It is also affected by the load impedance. Then, if I watch this as a terrain, so I would have the height proportional to the value of the error function. I would see something like a very, very narrow valley that is L-shaped. So I have a narrow valley which has more or less some bottom, and within this bottom there is an optimum, a point where you really meet the design goals. And this is very difficult for optimizers, and I will soon show you why. So even this is a very simple case. It is not as easy as you would think. You would easily solve that just having a variable capacitor and tuning it when listening the radio receiver. In fact, you would not need any more technology to do that. But if you have a circuit simulator, the solution of that is not that easy. So now, I have shown you what the error function is, why do we make it, and I would have to switch to the third important component in optimization, and that is the optimization method. So how to find a minimum of a function which is known but not evaluated at all points. We have some search space. The search space is mostly multidimensional, that is, it has the dimension of the number of variables. In that case, we had 2, capacity and inductance. So we have 2 variables, but we could have more variables, and the search space is created by all possible values of those variables. It could be continuous, it could be discrete in some cases. At the same point, the search space could be bound or infinite. Let us consider that for engineering purposes, you have always some bounds or limits. For example, you would not easily buy a capacitor of 200 farads that would work on high frequencies. You would never buy a negative capacitor or inductor. When there are dimensions, you would never fit a 1 kilometer transmission line into a mobile phone. So there are limits. The second point is that this search space is sometimes continuous, and sometimes there are some holes in it, some places that you cannot achieve. So Within this search space that is described by several variables, I would use the number v, and we know that the v is in fact a vector of v1, v2, v3, etc., like resistor, capacitor, or dimension, or for example property like permittivity or permeability of some construction material. And this, the task that is here for us is to find minimum of error function but the minimum is inside the search space, so inside all possible values of the variables. Now we can have several approaches. Some of them are, say, brute force and work. Some are less easy to understand but work better. Before I try to classify between those, I have to tell one important point. Mathematicians have studied optimizations very, very carefully, and then there is an important thing that should be known. For each optimization method that at least conditionally converges to a solution, there exists a problem that is optimally, that is fastest, solved by this method. So if you find out a very strange method, you may be sure that there is somewhere a problem for which this method is the best one. Well, this is nice. So anything you do is not useless. On the other hand, there is a thing we are less happy with. Although we know that the problem exists, we do not know which problem that is. And in engineering practice, you are mostly faced with another order of things. You have a problem and want to solve it. And you want a good method that does it. But unfortunately, there is no hint how to find it. So what mostly is done by people who write software for optimization is that they include several methods they are happy with, that are proven that they work for similar cases, and they let the user to try one or two or three or seven of those in a blind belief that one of them works. That's the situation, the state of the art of classic optimization at the time. I have to show another big problem of optimization in multi-dimensions. I will show it with a 1D graph only, but please consider that, for example, if we have a function and we search for an optimum, well, the ideal case would be that the error function of one variable would look like this. Then this is the optimum, and that's fine. We have been searching for a minimum of a function, and there is only one minimum. If the function is continuous, we can say, okay, the minimum happens when the first derivative becomes 0 and the second derivative is positive. Well, that's fine. But what if we have another function and it looks like this? And at this moment we can see that mathematically it has 4 minimums, of which we possibly would like to get this because it's closest to the goals, and still this minimum does not reach 0. Now for all of those minimums, the mathematical definition, that is 0 in the first derivative, positive second derivative, is true. So all those are minimums. We will call them local minimums, and the one of those minimums that has lowest value would be a global minimum. The problem is that this is in 1D. Just imagine this in 25 dimensions, and you would have a real problem to find out a global minimum if the search space is rather big. Well, there are methods that can handle this better, but that would be the scope of my next lecture of optimization. Let's say global methods. We are still working with the old local methods, and I just wanted to tell you that there is a possible problem, that you might find an optimum which is not that much optimal at all. Now what to do against that? Mostly you have to run, in a classic approach, you would have to run the optimization from different starting points several times, and hopefully you will find the best, that is global minimum, but there is no proof you did. From the engineering side, if you find a solution which is good enough, you are done. So local and global extremes, in our cases minimums, are important. And now I can start to tell you basic ideas of, let's say, 3 methods that would be possibly used in software, and you should know the key principles. The first method, called direct search method, is a kind of brute force method. It is quite tolerant to functions with a number of false or local minimums, and it works in a manner that I would demonstrate in 2D. So we have, let's say, a rectangular area with 2 variables, 1 variable, second variable, and we will try to find the optimum. So the area must be bound. This method inherently contains some bounds on all variable values. So the first step would be randomly generating points inside the search area. And to make this method work, you would have to generate a number of points. So for example, you generate 1000 points randomly. In order not to make a break in this lecture, I have been only marking some of those points from that 1000 pieces collection. Now for each of the points, we evaluate the value of the error function, and one of the points gets the lowest value. For example, this. The next step is, I decrease the search space, let's say to 1/2. Decreasing the search space to 1/2 means that I decrease, for example, with a factor of square root of 2, one dimension, and with the same factor the other. So let's say I will do this. So this is off. And at the moment I would generate 1000 more points. And I will find out possibly a new optimum or a new candidate for optimum. I will again cut the resulting space to 1/2 and repeat this procedure as long as I get to a very small set of bounds, and the last best point I have experimentally shot is my optimum, and that's the result. Now the method could be programmed possibly or 5 or 6 lines of code besides the error function. Of course, that's the tricky point, but the method itself is very simple. You can, of course, make a lot of variations with the shrinking ratio of the area and the number of points you generate in each step. Although it's very simple, it can give you, for simple cases, good results. Now you possibly wait for some but. Well, the but is, it looks very nice in 2 dimensions, but what about 20 variables optimized at the same time? Well, in that case, shrinking state space to 1/2 means only shrinking by the factor of 20th root of 2 in each dimension. So in fact, you would have an extremely computationally exhaustive method that would only slowly shrink the space, while you will not do with 1000 points in each step, because with a 20-dimensional space you would need several tens of thousands at least to make the method work somehow. So this is a kind of brute force method which works for a small number of variables, would solve this problem, for example, happily, but with an increasing number of variables it gets very, very slow and computer time consuming. But it could handle close to anything, non-continuous error functions and other things that are difficult for other methods. Brute force method, easy to program, with some performance. Your questions, please, to this method. Seems there are no questions, so I will now switch to another method which should be also very easy to understand, and that's the method using gradients. Just remember, a gradient is a vector that has 2 important properties. It points in the direction of increase of a function, and its size or magnitude is proportional to the speed of increase in that direction. To tell it in other words, if you do downhill skiing and if you want to go in the fastest possible way downhill, you just orient your skis against the gradient and go downhill. So in fact, a method like this would mimic skiing downhill in a way that here in Czech lines we call jet dolů šusem, to do the fastest descent against the gradient. But there is one important difference. If you are a skier, you just continuously watch the gradient. So if you go on a hill that has not an ideal shape of concentric circles of an ideal ball, you turn with the changes of the shape of the hill so that you still maintain the direction. Unfortunately, computation of a gradient is very exhaustive. It takes a lot of computational time. So a gradient method would not work this way. Now I will describe you a gradient method that is again a brute force one, does not work for many cases, and it's called a steepest descent method. So first, such a method starts at some point. And we would require that this point is inside the search space. Now we would have to start. First we evaluate the gradient at this point. Once we have that gradient, it could be easy if there is an analytic solution to the gradient. If not, for example, the task contains measured data, then we have to evaluate it somehow numerically, and that means to repeat the evaluation of the criterion or error function at least n+1 times, where n is the number of variables. At least, mostly a good gradient evaluation needs more steps. So if we have numerically got the gradient, we know that we have consumed a lot of computer time and we would not like to repeat that. So now, if we have the gradient, we will make a step. If the starting point was A and the gradient was G, so we will get a new step, A new, which would be the old minus gradient, we move against the gradient downhill, times some delta, some small step. And now there are two possibilities. If we just cut the function in 1D in the direction of gradient, we would possibly have something like this. We are sitting somewhere here and want to get there. So we make some step, and possibly the step was not long enough. We could possibly get an estimation of